everyone. Thank you for joining AI Horizons episode 5. AI is moving beyond perception. It is beginning to understand. In this episode, we explore how the next phase in enterprise intelligence is being shaped by visual reasoning. With models like OpenAI's O3 and O4 Mini leading the way, we'll uncover how AI is evolving from recognizing images to interpreting context, drawing inferences, and driving smarter decisions across industries. Joining us today are two leading voices in the field. So let's move to the agenda. First, we have Jianfeng Gao, a distinguished scientist and VP at Microsoft Research. He will take us deeper into the cognitive evolution of AI, exploring how models are beginning to reason, simulate, and even mentalize in ways that mimic human understanding. Following Jianfeng will be Satik Basha, who is an AI Global Black Belt at Microsoft. He will showcase real-world use cases and a demo, bringing the next-gen capabilities to life with applications across sectors. With that, let's get started. Jianfeng, over to you.
Thank you. Today we'll discuss some of the very exciting ongoing research projects, just show you what's possible in the near future. We know that almost all the revolutions in science that fundamentally change our lives start by asking big questions. For example, the questions about the basic building blocks of the universe, how life begins, and how to measure information, lead to the discovery of three of the most fundamental kernels of our physical and digital worlds and ourselves. Similarly, one of the most fundamental questions in AI is the origin of intelligence, or machine intelligence, if we believe machine intelligence is different from human intelligence. Right? Although we do not, at this moment, have a widely acceptable answer, recent advances in AI, in particular, the large reasoning models and the reinforcement learning, open new opportunities to explore the answer. This is the AI-generated answer to the query, what's the origin of intelligence? It's a very long answer. I summarize it in one sentence. That is, intelligence is obtained from interactions. Because of this, we group our reinforcement learning projects and Microsoft into three different categories, depending on how the AI models interact with different entities. In the first setting, these AI models interact with logical reasoning problems, such as math and coding, using prior knowledge and trial and error. The reasoning typically does not require any interaction between the model and the external world or users. Microsoft just released a family of highly capable and cost-effective reasoning models called file reasoning models, which are very small. Despite their small model size, they achieve similar or even better performance on math tasks compared to much larger reasoning models on the market. In addition to the development of file reasoning models, we have been focusing on two much more challenging reinforcement learning settings. One is to teach AI agents to interact with digital and physical environments. These agents learn to act by simulating or imagining based on an inner model of the external world known as world model, which often includes a state transition probabilistic model and a reward function. And in the third setting, AI models can simulate not only external environment, but also humans' mental state, ability known as mentalizing. These models need to learn to interact with users, infer users' intent, and behave collaboratively to win users' trust to become their AI companions to accomplish long-horizon tasks, such as tutoring and document generation. Now I use a figure to clarify these three abilities that allow AI models to have human-like intelligence. First is formal reasoning. This is performed by an AI model using prior knowledge in a stationary setting where, for example, the math problem is fully specified and fixed, and the answer can be easily verified, and the model does not need to interact with the external world or users. Simulating is very necessary when an AI model needs to select its behavior or action based on the responses from the external world, which is often non-stationary or very dynamic. Compared to learning to act by trial and error, as in the first setting, learning by simulating could be much more efficient and safer on the condition that we know how to build a good world model. Mentalizing is important for any AI models that interact with humans for collaborative tasks. The use of user model, like the world model for simulating, is critical to efficiently capture user preference and inferring user intents. Now I brief the project that aims to teach AI agents to act by imagining using the world model. And the model framework we use is called deep dive. This is an extension of the dive method of combining model-free and model-based reinforcement learning method proposed by Richard Sutton in 1990. The deep dive architecture is shown in this figure, where I really want to point out a few key elements here. First of all, we notice that the initial world model and policy model are trained using pre-collected interaction data. Then the real experience here, which are generated from the interactions between users or between the agents and the environments, are used to improve the policy model by direct reinforcement learning and the world model by supervised learning. So the real experiments, although it's of very small amount, are fully leveraged in this setting. Then the world model is used to both test time action selection by test time planning and the policy learning by background planning. And the policy is revised using both real experience. Here, real experience is generated by interactions between the agent, the real world, and the simulated experience. This simulated experience is generated using the world model. So sometimes people call this algorithm weekend sleep algorithm, and similar to human beings, how we learn things, right? When we are awake, we experience the world, learn from real experience. When we are sleeping, we dream of a lot of things. It's like the simulation part here. And DIE, as I mentioned, the DIE method is proposed in 1990 in a tabular reinforcement learning method, as a tabular reinforcement learning method, which applies only to small-scale game tasks, such as the maze here. Sutton and his colleagues are able to show that a DIE-Q agent that integrates planning using a world model is up to 10x more efficient than a non-planning agent to learn an optimal policy. But this setting is very limited. It assumes that you have you can enumerate all the states and actions in the environment. It's not very realistic. To build real-world agents, we really need to extend this DIE-Q method to deep DIE-Q by using deep neural networks to represent infinity state action space and use prior knowledge encoded in pre-trained large-scale language models. This leads to our new approach called the deep DIE-Q, right? Or simply we can call this deep dive. Here is the results of DeepIQ agent for task-oriented dialogue, where the state and action space consists of any natural language text. Thus, the space is extremely large. And this DeepIQ or DDQ manages the state action space by using neural networks to represent the natural language using low-dimensional vectors. Similar to the experiments of tabular method, IQ, we show that DDQ that integrates planning is significantly more efficient than a non-planning agent for dialogue policy learning. Now let's see how we leverage the prior knowledge encoded in the pre-trained large language model for DeepIQ. We noticed that most of the state-of-the-art reasoning models, such as R1, DeepSeek R1, can already propose possible actions and simulate user outcomes during reasoning. Consider this task, right, of creating a detailed report of all purchases made in the last 6 months, and the current state of the model is on the Amazon homepage. Okay. So now the model is on the homepage. See on the homepage, the model needs to select the next step, so that the model eventually can create the purchase report. And there are 2 possible actions. One is that I can click anything in the homepage. I probably the website will show me something. But the model think about this in his mind without actually taking the action, but found that it's unlikely. The model can obtain a report by clicking anything on the homepage. Then the model try some different actions in mind. And so, oh, how about I move to a different page and click return and order menu. Probably this time we can show some report, and the model believes that, oh, this probably is the right way to write next action to select. So the model do this. We show that these large-scale models, by training on large amounts of data, especially web data, already have some capability of simulating the real world. But the problem is that the simulation is very poor, because I cherry-pick some good examples. There are a lot of bad examples, which can lead to bad results. So all we need to do is clean up the training data, meaning that given the R1 generated the chain of thought reasoning tokens, can we identify what part of the simulation is correct, what part is not correct, or even not irrelevant, not relevant? Then if we clean up this, we already got pretty good results. So this technology is called distillation. Okay. As I mentioned earlier, traditionally distillation is done by just generate all the training data using big model without any filtering. But here, since we know that we only care about the simulation part, so when we get the model generate data, we return only the relevant simulated cases from the trained data, and we train the model using that data. We can get much better results. This is the first step for the distillation. After distillation, you will already have an initial model, which is pretty good. Then you can deploy the model in real world. Then the model will continue to learn to improve itself through reinforcement learning. And during reinforcement learning, if we can ask the model to learn not only how to predict the next action, that's the policy model, but also predict next state based on the action, that's the world model part. So you ask a model to jointly learn both the world model and the policy model, then it achieves much better results. So combine both, we demonstrate that the DeepIQ can generate much better results, obtain much better results than all the competing methods. This is the test results on the computer use tasks, both in out-of-domain setting and in-domain setting. Now I want to show you some very interesting idea we explored recently. Now we know that we want to build a world model. The world model will predict, will simulate the real scenarios. Okay, if you click from a button, what's gonna be the next web page? But sometimes the world model can make mistakes. So how to improve the model so that the model can make less mistakes? One way to improve model is to train the model to be able to judge itself. This is based on the idea a good simulator always knows how good it can simulate. Then this is the example illustrating how we generate training data for such a model. For example, given such a task, we can run the task in the real world setting so that at current state, this is the current state. And if I ask a user to click a U button, then it moves to the next state. Then at the same time, I can use the world model to generate the next state. It's a simulated next state. And in case that the simulated next state is different from the real next state, then I ask another model, let's say the GPT-4o, to generate comments on the difference between the simulated state and the real world, real next state. This is the comments generated by the model, the judge model. Now, given all this data as training data, we can train the simulator itself to not only generate the next simulated state, but also comment on the quality of its own generation. By doing so, we significantly improve the quality of the world model. This is another project. We know that in the real world, another thing we need to deal with, a challenge we need to address is multimodality. This project called Magma aims to develop foundation models for agentic applications in both the digital world and the physical world, including web browsing, robotics, and autonomous driving. This model is trained from large amounts of video data. And here, each video is processed to form a trajectory of state action pairs, as I showed in the previous slides, for solving a task, which is described, the task itself is described in the capital or subtitle of the image. Then we also label the objects in the videos by object IDs and the moving objects by video trace. Let me see if I should, can you see this? For example, we trace the moving of the objects here. Yeah, as a result, the model can learn not only how to make the action plan, but also how to take actions in the physical world and digital world to complete the task. Now here's a few demos to show how the Magma powered agent in action in different settings. Consider this one particular setting. Oh, I hope I can show this. Okay. Somehow it doesn't work here. Yeah, this one which shows that the Magma model is used to drive a robot in the physical world. You can see. Drive the model drive the robot in the physical world to pick up the brush, and then use it to swipe the coin into the sink. Yeah, somehow it doesn't show here. We have more demos afterwards, don't worry. Now we consider the third reinforcement learning setting, where the agent must not only interact with the environment, but also engage with users to detect users' attention and preference and guide the users through a sense-making process to help them clarify their true objectives and the designs. And such setting is very common for many user-centric real-world tasks. For example, here, take document generation as an example. We often envision in the scenario where user provide a detailed instruction to the AI model from the very beginning, or the user, we assume the user already know very clearly what to write in a document. However, in reality, users typically start with only a very rough idea of what they want to write. They engage in the writing process and discuss their ideas. The details gradually become clear and more refined. So it's more like this setting. You need the user need to discuss with others. In this case, it's the AI agent to clarify what exactly he or she wants to write in the document. Then the project we have been working on is called Collab LLM. Our goal is to enable an AI model to acquire collaborative skills through reinforcement learning, enhancing their ability to collaborate with users effectively. We began by training a user simulator, like here, user simulator, using data and user profiles to mimic user behaviors. Then we develop a multi-turn reward function that predicts the future benefits of specific actions through forward sampling. For instance, it can determine if introducing a new perspective in a discussion would enhance users' satisfaction with the document. And this reward function, combined with the simulator, guides the AI model in selecting the most effective actions to collaborate with the user to accomplish the design, to achieve the outcome. Yeah, our model was evaluated through a user study involving around 200 participants, and it significantly outperformed competing models in terms of user satisfaction. Participants noticed that our model excels at clarifying user intents by asking insightful questions and prompting considerations that might not have been previously thought of. In addition, it aids in writing by guiding users on what to say and identifying necessary information. And the model is also evaluated in other collaborative tasks, such as coding. For example, when a user requires to tokenize a text file and the task is inherited open-ended due to unspecified factors like the NLTK environment, tokenized selection, and optional pre-processing steps. While a baseline language model, as I show here, makes several arbitrary assumptions, such as applying the lowercase conversion and the stop or removing, even without user's confirmation. Our model here actively seeks to clarify user intent by confirming key decisions, ensuring an aligned final solution. Actually, this technology has also been incorporated into the deep research released by Microsoft recently. If you go to the deep research agent, the agent will first ask you a bunch of clarification questions before generating the report. Now I'm gonna show you a demo, which is called Deep Garden. This project is in this project we're developing an AI agent that assists in early stages of gaming prototyping through an interactive sense-making workflow. Bears?
This is a video demonstration of Dream Garden, a design assistant for generating open-ended simulations in Unreal Engine. So the first thing the user does, which we're seeing here, is they'll create a dream node. Here the user's talking about cows being abducted by a spaceship, and they're describing this in quite an open-ended free-form way. So once the user's satisfied with their dream node, they can begin to step the system. And here what happens is the system has reformulated this initial freeform idea into something a little bit more structured. And then from this high-level description of the simulation, it's broken down a number of high-level implementation steps. And this planning step is applied recursively. Now we're going to let the system run here. Let's now look at what the system did a little bit later. Here it was working on implementing the spaceship and its flight patterns in particular. And so let's compile and run the project as it was at that point in time. So here we are in Unreal. We have a spaceship, and this was a mesh generated via diffusion. And it is moving in the sky, and it is on a flight path into and through the ground. Perhaps not the most reasonable flight path, but it's a start. Now let's jump to the final attempt node that we have in our UI here. And run the project at that point. So here we can see that there are primitives on the ground, which correspond to the animal actors. And the spaceship is hovering above them, and it does seem to have lifted one of them out of the air. This green debug sphere, though, is kind of an eyesore. So we're going to jump into the code and just comment out that line. In Unreal Engine, we have much the same thing as before, but you see that debug sphere is gone. One thing that's still clearly off, though, is that we're using primitives instead of the cow asset, which you can see the system generated right up there. So here we're going to add a new coding node, and inside of it, we're going to provide some encouraging feedback to the system. And we're going to ask for it to use that cow asset or perhaps the sheep asset. And in order to specify which coding attempt we're responding to, we just drag an edge here from the generated code to our feedback node. And then we'll step the system. Once it's compiled the newly generated code, the system launches an Unreal Engine to run the simulation and collect screenshots for self-evaluation. But here we've stepped in just to check it out ourselves. And we can see the situation on the ground is that the cows are now proper colored and textured meshes. And when we hit play, they are going places with one unlucky cow being lifted into the sky by a spaceship. Let's look at some other ways that the user can interact with the system. And so we've rewound a bit here. And looking at these leaf nodes, we notice that there's one that says generate other animal assets, but then it's marked as a diffusion mesh generation leaf node, which means that only one asset will be generated. But maybe we want sheeps, pigs, and chickens in our simulation ultimately. So let's uncheck this leaf node toggle and then run the system. And we can see that this node, now no longer a leaf, has been broken down into subtasks. And jumping ahead a little bit, we can see that the system has generated those meshes for us for later use. Conversely, if we think of that last user interaction as the user watering a particular part of the tree, forcing it to expand, then the user can also prune the tree. And so just for the sake of demonstration, we've had the system expand this task of generating a chicken asset down into subtasks. And this is something that we noticed happening several times while developing the system, which is that it will do exactly this, kind of breaking down the task in too much detail. Here it's saying it's going to separately generate a text description, then generate the asset, then import the mesh into Unreal. But as we've seen now, this is all, of course, automated by the pipeline already. And so this node can be a leaf. So we'll check that leaf node. And having resumed the system, we can see that that chicken generation node is once again a leaf. So these are some ways where we allow the user to interact directly with this tree-like graphical representation of its processing. And we noticed in our usability study that users were particularly engaged while watching the growth of the planning tree. And so beyond just pruning or growing the tree, there's a lot of ripe opportunities for allowing users to, for example, edit plan nodes, add or delete them, merge them, or even create a new root plan node that takes input from coding attempts from a previous tree, say. allowing the user to engage in a kind of high-level, long time horizon dialogue in which they push the system to generate increasingly complex and novel simulations.
Yeah. In this talk, I've provided an overview of our ongoing reinforcement learning projects aimed at developing advanced AI models that extend beyond formal reasoning, such as in math and coding, to encompass simulation and mentalization. Therefore, we really hope we can achieve more human-like intelligence in the near future. These models are capable of simulating scenarios, understanding causalities, and even inferring and predicting human intentions and emotions. Our approach involves extending Richard Sutton's the IQ measure to a large language model powered reinforcement learning architecture that integrates user environment models for planning, aging policy models for action, and wake-sleep methods for model learning. We have validated our approach across various agentic tasks, including dialogue, computer use, and human-AI collaborations. And our results demonstrate that this new model significantly enhanced the learning efficiency of AI agents. Yeah, thank you. And back to you, Vera.
Thank you so much, Jen Feng. I love hearing from Microsoft Research. I feel they always bring such knowledge to the industry. So thank you so much for your presentation and your demo. Another thing we love is demos. So with that, I'm going to hand it over to Satik, who will go straight into some demos for all of you.
Thanks, Vera. Thanks, everyone, for joining. So Jen was talking about all the advanced reasoning models and how it works. Now, if we put it in action, what are the low-hanging use cases that we can solve right now in the enterprises is what we are talking about. So as you see on the slides, these are some real customer use cases that have already started making use of O4 reasoning. And we see the results that is much more efficient in their use cases. So first, like we talk about the use cases where across the industries, one across the transportations, for example, the use case that is listed out is an airlock safety detection. So this is a very critical use case because the airlines cargo bellies have to lock the containers before these containers go for the flight. But these operations are done manually and human evaluation is done on the pictures, whether the locks are properly engaged. But oftentimes, if it is missed out, it could lead to a huge loss. Your traditional vision models could detect the objects, but it would not be able to reason out based on the locations properly. So that's where this O4 reasoning or O3 mini reasoning, all these, even the smaller models are working efficiently in terms of identifying that use cases, those scenarios. And second, about like we see a pattern around the infrastructure companies where they are trying to make use of the vision models to compare the 3D designs or 2D designs of the BIM models. It could be structural designs or it could be like wiring designs. But oftentimes, this involves designers to go through a lot of iterations and they look at the CAD drawings and annotate it. Right now, the current practices is to annotate the CAD drawings through the clouds and then pass it on to the reviewer and compare it. And if it's a huge infrastructure projects, oftentimes there is client comments or vendor comments. There are multiple parties who involved to finalize the design. So these might miss out a lot of comments or a lot of specification. On top of it, it's a highly regulated industry. It's a traditional industry. You have project specification plus the regulatory compliance that need to be met. For example, if there is some car parking or if there is some free space that should be left out around the infrastructure buildings, those needs to be detected properly in the vision models. So, but if you go with the traditional practices, you will have to identify the individual objects which might miss out the spatial understanding of what this plan talks about and also what the compliance requirements are. And I will talk about only first three use cases which are more prominent. Another one is like a health and safety scenarios where there is a huge requirement around how do we there is already a lot of workplace safety monitoring systems which identify whether the workers are wearing a PPE kits or whether there is any safety incidents happening. But if you notice, the current workplace safety monitoring systems often produces a lot of false positives that they get either desensitized or they have to neutralize those alerts. So this is where vision models comes in place with the reasoning ability, where you pass out the filtered events and make a confirmation around whether that event is really a safety incident that need to be monitored and action should be taken across that. So again, there are more use cases where in retail, if there is a monitoring where you have CCTV cameras monitoring the inventory, that could be a system which could understand this spatial understanding what is available in the in your stocks, and then it could also optimize your inventory. So being a reasoning model, it is able to identify the objects and also link up to your optimization planning aspects as well. So like what of scenarios can also be incorporated as part of the reasoning pipeline. And of course, the manufacturing industries have these, for example, PCB boards. The quality is a critical aspect, but there could be a tolerance around what needs to be fixed for the quality control and what can be tolerated. So that reasoning ability is what is critical in terms of controlling the cost or even improving the productivity. To demonstrate a scenario around that, let me get into a video to show you how this actual use case works for an infrastructure scenario. So I'm not taking an infrastructure scenario, but here it is more of a real estate scenario where a real estate agent has to analyze multiple plans to find out his potential customer profiles, and also if there is any design change that he needs to provide for the design team, and whether the design adheres to the compliance requirements of a particular municipal. So in this case, I put out a simulated scenario of taking the Johor regulatory compliance, and then I'm taking in a race of ethnicity Chinese, and then putting out an age group and family size. I have uploaded a 3D floor plan, which is kind of like this, which is the 2-floor semi-detached house with a 1-bedroom plus master room plus working area plus a sauna and all the facilities. So the system is now fed here. The model that is run at the background is O4 Mini, wherein it takes these floor plan and tries to analyze it and provides a structured output of what might be a possible design considerations and what is possible changes that need to be done for a profile that prefers for a feng shui. So in this case, I put out a cultural preference of feng shui, but if it's an Indian, the model has the worldly knowledge of Vastu, or even if it is a contemporary design, we can set the cultural preference. Basically, it all goes as part of the prompt, and then model generates. So in this case, I'm just putting out the house dimensions because this flow diagram is as a mock diagram from a public data set. And as you can see, this analysis would take time. I'm just fast forwarding this, and you could see it. You can build a pipeline that can provide a structured output around it. So, for example, it provides a summary of what the whole design talks about, whether there is a compliance or there is some changes needed, and what is the cultural fit around this particular design is. Like, for example, in terms of cultural assessment, you can see that it is able to identify that the kitchen is in the east sector, but the stove is on the center east rather than the west corner. So it is able to locate where the particular component is, and also able to match it to the feng shui requirements that we have put in. Like, it's just a preference, but we are trying to identify the demographics who can be a potential target for this. Like, if there is a CRM system that knows about the customer profile, the users would be able to, the real estate agents or the developers would be able to relate to that. So in this case, for example, it says that the kitchen might not be in the right position, and it is able to, as you can see, it is able to identify the main entrance, and it is facing the south. I have not defined anything on this particular diagram. So I just took a mock diagram and then set out direction. Okay, this would be the north. Then it is able to identify what is the main door and which direction it is facing, and is able to locate all the components in the right directions. So likewise, like once we have these results, like you can see that it could also get into an ideal customer profile. And also, as you can see, it provides a demography of which GUA can be targeted for. Like it could be a best fit for number 2, 7, 8, and 9. But of course, the system is also recommending what kind of suggestions that could be made, like in terms of design. And this is where it might add more value around how you can use the reasoning models to generate a design. A lot of these aspects are not tapped on by the customers, but you can even generate a SVG image from a reasoning model. So in this case, I'm just trying to simulate a scenario where if you have a design and if you know the design instructions, you can try to generate a SVG image and provide a recommendation around it. Say, for example, the kitchen island was in a different direction, but after the design change, you can produce an output which says, okay, this is what the possible design change that might be more applicable for the feng shui requirements that we made. And so far, have to be moved to a solid interior wall facing the entrance. So it is recommending, and it is able to identify the direction and the settings that it needs to produce as well. And of course, it also produces the clarification questions. In this case, for example, it is not able to get the year of birth for the client. Maybe that would help you to narrow down the demographics as well. So you could see how you could make use of the reasoning models to construct the whole application around that. But let's get into an action of how it is actually seen in reality and how you would like to test it out on Azure Foundry platform. Of course, Azure Foundry platform is our unified platform with all possible options that you need, tools and services that you need for building any GenAI application, specifically GenAI. And also it allows to customize the models, create workflows, manage AI application in a unified environment, and you get different type of playgrounds to test out your scenarios. In this case, I just put out the same prompt that we used in that application. Basically, it is a prompt that says that your intelligent assistant reporting on the real estate. Here I'm using O4 Mini, and I'm providing a responsibility on the regulatory compliance check and also these instructions that we usually do with the prompt engineering. The prompt engineering is a very critical part. We don't provide the chain of thoughts and reasoning, but we provide how the persona of the, what is the persona of that application should be, and as well the output format that you are expecting out of it. So in this case, I'm just providing the instruction around what the design specification should be and what the structured output should look like. Of course, this reasoning models are not meant for a scenario which is real time. So these analysis would actually take a little longer. And to save time, I have already generated a similar scenario where in this case, I just changed the direction of it. Last time it was facing this side. I just made a correction around changing the direction, because usually the flow diagrams do not have the north direction on this side. So the model is able to evaluate. This is the most important part. Like with GPT-4o models, you don't get the how it is being evaluating. For example, if you need an explainable part of it, you don't get the responses are slightly longer in O4, but it adheres to the requirements. But in normal LLMs, they tend to provide direct answers with very minimal explanations. If you have added in the prompt saying that you need more explanation around the results, you would get it, but it would not have the chain of summary. It is, in this case, if you see that it is evaluating the house design, clarifying the door orientation, and it is also determining the entrance and also evaluating the orientation, but it sticks to the principles of what we are putting out in the problem. And this is not the final result you get, but how the pipeline usually you would construct if you had to build an application around O4 is that you get this output and you don't overload the model with providing the final output. So basically you can use this model, feed it to another model and provide a JSON summary. It could be any model. It could be O4 mini or GPT-4o mini or anything. And one other important fact that I want to highlight is that O4 mini is actually 50% cheaper compared to GPT-4o at current stage. So which means like you could make use of a lot of non-real-time scenarios with the advanced model and you could get a better results out of it. GPT-4o mini has been released, like it has been there for more than a year, but O4 mini has been there for a few months, but the price is lower with higher capabilities around it. So in this case, I provide this structure output, which is what you have seen over this set of sections that you provide in the output. And as well, once you have this output, the other aspect that I was trying to show was on providing the SVG generation. So as you can see in this case, I provide instructions again to the O4 mini, asking it to be a SVG file generator. Basically, I provide the dining instructions and ask it to generate the raw SVG plus the change in SVG design. So this is what you saw finally as a design in this case. So like what you saw here was an SVG that was generated from O4 mini. Right. So this is how you build a pipeline around the reasoning. You feed it. It is having the spatial understanding of what the image does, what image contains. And it is able to provide multiple varieties of how the output should be with spatial knowledge around it, and plus the worldly knowledge that already the normal LLMs and the O4 already has. And most important part is like, if you want to have the chain of thought processing, you would get it as part of your SDK responses, which you can put out in your explainable AI portion of it. The governance is the most important thing. So you would, in your applications, if you need the chain of thought process, you would get that, and you would get to have a better understanding of how the model infer that results. So we talked about the infrastructure. So in an actual scenario of larger infrastructure question, I also want to talk about how it is done in an actual scenario. For example, if it's a huge infrastructure design buildings, for a design change analysis, you would always need to augment traditional ML principles. Like in this, for the floor plan, yes, of course, we uploaded it to showcase the O4 reasoning abilities, but it gets much more powerful if you take this drawings and add the flavor of computer vision techniques. Say, for example, in this case, what I did was I took a open source available BIM diagram to enact the scenario where if there is a design change over here, basically you would remove some of the parts or you would add the spots. So in this case, I just removed some of the components and the struct availability. And then what we do is we usually pass it to an SSIM, which is just a technique about the structural similarity index measure. So if you have this additional information, this is where the model gets much more powerful because it has the more details around, more information around the context, what it needs to provide. Usually these drawings are very big and you will stitch and slice it before you pass it to the O1 model. So these additional information gives it more context and provides a better responses. That's where the next scenario is around, as I was talking about, the arrow lock scenario. So if you have a arrow lock one, so this is a typical picture that I taken with inside a cargo plane, where these containers have to be latched, locked, and fastened and raised. If it is locked but not raised, it is still a safety issue. So what happens in this pipeline is that basically these models are trained using large set of images, not large set of images, using custom vision. There is a set of models that tags this object detection, which you primarily do with your object detection systems. And it tags those models, tags those objects, but what we need to focus and pass these. And also I use another computer vision techniques to enhance the image and pass it to the model to get the better responses. But if you can notice, this is a result from GPT-4o. It sometimes picks it up 4 images, sometimes it takes it out as only 3 logs. This is where you need to see that how powerful the O4 or reasoning models are. In this case, I'm asking the models to produce the number of logs raised. It has wrongly identified 4, but sometimes it would rightly direct it as 3 models. So if I do the same scenario over here, what you would get is, like, for example, if I have to take the computer vision outputs where the objects are already tagged and ask the model to come out with the safety evaluation, it would be able to come out with a much more structured output, like how you would. It is going through the JSON structure format, and it is just analyzing chain of thought. Process will come to the results, but what you would get as a result is something very similar to this. Like, it is able to identify the each logs and also provide an identification around it, and reason out if I have put out an instruction saying that if your confidence is lower, provide a reason why you think the you have a lower confidence around those results. So you see, we just got the similar results for the same image, and you can see that it is able to give much more structure output. It's consistent with in terms of the number of logs it identifies and in terms of the scores it detects. So this is another scenario where safety instructions are critical aspects. And talking about reasoning models, of course, images is one aspect of it, but there could be other scenarios where you would need videos to be analyzed as well. That's where you might have a new service within, most of you might know, but there is a new service which was introduced a few months ago, which is called content understanding. This content understanding is a multimodal AI service provider off the shelf. It does the video analysis, which is not designed just for video analysis. It can take any type of inputs, whether it is a document, image, audio, or even a video. So if you need to build such a pipeline, you will need to have different models. And if you say, for example, if you have to analyze a video, then you will have to slice that into individual frames and process it, and then get a summary out of it, and then identify the objects and brands. But this content understanding is a service which does all in one. Like, it is available as an SDK. It's not a SaaS solution where you need to upload it through the portal. It is available as an SDK as well, where you upload an image. This would take time, but actually, as I said, the reasoning, all the reasoning models are not meant for real-time inference scenarios. Whereas if it is a near real-time, or it can wait for a few minutes, then definitely reasoning model is the go-to place for the next set of AI applications that you're doing, or if you are upgrading your existing applications. So this content understanding is a service where I'm trying to define a set of schemas. Say in this case, you can define a set of fields. This is how it works. Like, you upload a video file and you instruct the system to define the set of fields. Like, if you want to have brands to be identified, identify brands mentioned in the video. And if there is some technology topics, you want to identify technology topics. You can define such fields, and the model would be able to so this is how you generate. Like, so basically you define the field, design the schema for what you want to provide as an output. And basically, once the data is analyzed, this is the kind of results you will get over the SDK as a JSON request. And for a visual perspective, as you can see, this is a 43-second video, which talks about the TTS and it talks about the data centers, where how it requires lots of data, and where it could be useful, for example, in terms of flight simulation, in the ground staff communication. This kind of speech recognition could be used. So it's just a video talking about the advancement of the speech models that is coming out. So if you see that the system is able to identify the right number of shots, which is there, and it is able to identify in each scene what you ask the system to identify for. So it provides a summary, it takes in the time frame, and in some scenarios, it is able to identify the brands as well, as mentioned. So in this case, like during the 7th second, the user mentions about the person on the screen talks about like the Microsoft Azure AI. So it is able to identify the brand, and also it is able to identify the technology that is being talked about. So you see in the case, this is the transcription of the video. And for example, if I go to scene 13, you can see that this is scene 13 at 35th second. You would see that it's a flight of, it's an Airbus. You just briefly see that it is an Airbus, and the system is able to rightly identify this Airbus. And also it is able to locate it. It is an airport, and of course, as with other things, like it would be able to identify the technology. Say, for example, in terms of 40th second, it's able to identify the technology that it is being talked about, aviation. So the reasoning models reasoning abilities are inbuilt within this application. So it is able to, you can use it off the shelf, call an API, and just use this model for all the video analysis where you need to have a media management or a content discovery or a faster content creation as well, like for highlight the generation and provide a summarization, which can be fed to existing RAG systems. So back to the slides, what we were talking about is on the we talked about several scenarios, and these are some architectural patterns you would see. Like for the cargo scenarios, as we say, you would need to augment the reasoning models with the object detection models. Like in terms of custom vision, you can use a custom vision, which Azure custom vision is quite powerful. You can use just 10 to 15 images and create object detection models and provide that as an additional information for the model to provide a better responses. And if you talk about the next architectural patterns, the next slide, if we talk about it. So this is more of the infrastructure scenarios, what we are talking about. There is a compliance document. There is some client review documents, which needs to be part of the prompt or part of your pipeline. And this image analysis, which in this case, this architecture talks about providing a CV techniques, computer vision techniques, and documenting that to provide a better response in terms of the reason. And also, of course, most of the times you try to make use of the GPT-4o models to provide a lower tasks, like low-hanging tasks, like the formatting of the outputs, or even providing some summarizations around the reasoning models chain of thought process as well. So you could use the combination of these two models and provide a more structured applications to end users. Thanks, everyone. Back to you, Vera.
Thank you so much, Satik. I think that was great. It really helps make our technology more real and industry specific. But to recap on today, so we explored how AI is really advancing from simply seeing the world to truly understanding it. We looked at reasoning, we looked at context and interpretation. We looked at groundbreaking research to really real-world applications. Visual reasoning is really opening up powerful new possibilities across industries. And as we continue to push the boundaries of AI, we do really invite everyone who's listening to stay curious, stay engaged, and really explore these capabilities that can transform your business. So what can you do to learn? On this slide, you'll see 3 things that we would recommend. First of all, experiment in Azure AI Foundry. You saw Satik already showcasing a demo. You can do that too. You can already open it up and explore AI Foundry today. Next, skill up through the Microsoft AI Engineering Learning Path. This is free of charge. You can just look it up online and you can actually get certified as an AI engineer. And then lastly, there's lots of news. We actually had Microsoft Build not too long ago. So I would recommend staying close to the news because technology goes fast. And it's good to know what is the latest and greatest on our tech space. All right, guys, thank you so much for your time and listening in. And we hope to see you on the next one. Bye-bye.
Yeah.